So I have the function 1 over x squared plus 1 the whole squared, okay? And I want to take the Fourier transform of it using the residue theorem. So the first thing I will do is find my poles. So we'll set the denominator equal to 0. So x squared plus 1 is equal to 0. And I get that x is equal to plus or minus I. Now we have a pole of order n is equal to 2, okay, because the denominator is squared. So we know the formula to calculate the residue for poles of order n. So it's 1 over n minus 1 factorial times the limit as x approaches our pole times the nth minus 1 derivative times x minus our pole to the nth power times our function f of x. Here f of x is of course our entire thing inside the integral, because we're taking the residues of the entire thing. Okay, so I mean we're taking the Fourier transform of 1 over x squared plus 1 the whole squared, but to take the Fourier transform using the residue theorem, we need to consider our entire thing inside the integral as our f of x. Okay, I hope it's clear. I mean it's maybe obvious, but I just say it. So now here is n is equal to 2, so I have 1 over 2 minus 1 factorial times the limit as x approaches our poles. So in this case plus or minus I times the first derivative, okay, 2 minus 1, so 1. So the first derivative times our x minus plus or minus I squared times our function, okay? So our function e to the minus I omega x over x plus I squared times x minus I squared, okay? So now I want just to be careful, because we won't consider both poles in each case. In each case, we have two cases. We will need to distinguish between if omega is greater or smaller than 0. And depending on the sign of this omega, so if it's positive or negative, we will need another pole, because we will need another counter integral, okay? So if omega is negative, so smaller than 0, we need to make to have a counter integral that is along the upper half circle, okay? So we have our counter integral which goes from minus to positive infinity, and then we go along the upper half circle, okay, with the radius that tends toward infinity. So in this case, the only pole inside the domain is I, okay, because negative I would be like here somewhere, and it's outside our domain, so we don't consider it. And so our only residue is that x is equal to I, and so we can use this entire formula here, I said, but only for x is equal to I, okay? So only only x towards I, okay? And so if you use everything also here, we only have x is x minus plus I, okay, so x minus I the whole squared, okay, so we can cross it out with this thing here into the denominator, okay. If it would be x minus I, we would cross it out with this one, okay, because it's minus I, so plus I, and so we would in this case cross it out with this one. That would be the case for the other case, okay, so the second case. But first, let's finish the first one. If you compute everything, you should get as a residue 1 over 4 times I times e to the omega times omega minus 1, okay. And so also here I want to point out that e to the omega, we assume that omega is negative, so in fact you have a negative exponent, not a positive one. And that's already a good sign, because we need the whole thing to converge. So to converge, we need generally with the Fourier transform using the residue theorem, we need an exponential decay, so e to the minus infinity or something like that. And so you can already make sure that if you have something to the e to the minus something in your residue result, you're already on the good path. It's already a good sign, because it should be like that, okay? Yes. For the second case, you can see already that we have e to the minus omega, but here we assume that omega is positive, so it's okay. We just want e to the minus something in the residue at the end, okay? So for the second case, I said where omega is greater than 0, so positive, we need to integrate along the lower half circle, okay? So from minus infinity to positive infinity, then we go clockwise around a circle with again a radius that tends toward infinity, but this in the lower half plane, okay, where the imaginary part is negative. So below the real axis. And so our only pole in this case is negative I, which would be like here somewhere, and our I would be outside it, so we don't consider it. So our only residue at x is equal to negative I. If we plug in again everything in the formula, this time I said with negative I, so like here x tends towards negative I, and here we would have x minus I, so in fact x plus I, the whole squared, of course, and so I said we can first start with this part instead of this part here, okay? And so we get at the end 1 over 4 times I times e to the minus omega times omega plus 1, okay? And so that is our residue if omega, the sign of omega is positive. So now what you want to do is you want to prove that basically if you look at it, you know that the part of the contour integral along the real axis, so from negative infinity to infinity, is your original integral, okay, because we're going from negative infinity to positive infinity. And now we want to prove that the part along the semicircular axis, okay, so the part inside the imaginary plane, so not on the real axis, that this part, so the part number 2 here and 2 here, that it vanishes as the radius r gets larger and larger, okay. So as said, first we will do it for the omega is negative case, and the omega positive case is quite similar. So as said, the part along the real axis, which is our part 1, is our original integral. Under part 2, we will set x is equal to r e to the pi I t. Okay, why? Because r is a radius that will tend toward infinity, as said, and e to the pi I t, remember e to the theta I is a circle, and so e to the pi I t is also in a circle. It is an entire circle if t is between 0 and 2 or 0 and negative 2. But here we will let t be between 0 and 1. That means that we're going from 0 to negative 1. So it will be at a half a circle, and the half circle in the upper half plane, okay? Where the imaginary part is positive, basically. If for the second case we will let t be between 0 and negative 1, that means that we will go along the lower half plane along the circular axis, okay? But first, for the first case, so I really hope that you understand what I'm saying. So t is between 0 and 1, so we're going like this. Okay, that's the path here. That's what we're doing. Starting here, we're going here on the other side, along the upper half plane. So our dx is also equal to, well, we can take the entire derivative of everything. We get pi I r e to the pi I t dt, okay? And so we can plug everything inside the integral. We have the integral from 0 to 1, okay, because it's with respect to t, which is between 0 and 1. We can plug in everything. And the thing is, we don't really care about the dx and everything else that is not the e to the minus I omega x. Why don't we care about it? Because we want to prove that the second part vanishes, and to do that we use generally an exponential decay, as said. So we have e to the minus infinity, because the exponential decay wins over everything else. And so we want to prove basically that this e to the minus I omega x, where x is substituted with this r e to the pi I t, that it is similar to this e to the minus omega, okay? And so, yeah, we can plug in everything, but what matters basically is this e to the minus I omega x, where x is replaced by this r e to the pi I t, okay? So if we replace this x by this r e to the pi I t, we can then use Euler's formula. We know that e to the theta I is equal to cosine theta plus I sine theta. So we replace this e to the pi I t with cosine of pi t plus I sine pi t, okay? Why? Because we have an I here, and everything else that is not the I is our theta, so it will be pi t, okay? So we have e to the minus I omega times r, the r is here, times cosine pt plus I sine pt, okay? So now we let the omega and the r outside, but we will take the negative I inside. So you have negative I cosine pt plus negative I times sine of pt. So we have negative I squared, so we have negative 1, so we have positive 1, so we have sine pt, okay? And now, as said, we assume that omega is negative, so it's below 0. And we know that r tends toward infinity, so the radius tends toward infinity. And you know that sine of pi t is greater than 0 for all t between 0 and 1, okay? If you just look at the axis, you know generally that sinus is the y, and cosine is the adjacent, and the sine is the opposite, okay? And if we are going along a path along the upper half plane, so the cosine can vary, of course, but the sine is always positive, okay? If it would be in the lower half plane, it would be negative, okay? But here, for our case, if we go along a contour along the upper half plane, sine is always positive, okay? I really hope that you understand what I'm saying. It should be really obvious, but maybe it is not. And yeah, but if it's not obvious, it will come with practice. That's not a problem. Or we know that our e to the minus I cosine pt is bounded because there is an I here, okay? So it's again something like e to the theta I. And so, yeah, we know that this e to the theta I is bounded. It is bounded by 1. If there is another radius in front of it, it would be bounded by this radius. Okay, I hope that it's clear. So the e to the negative I cosine pi t is bounded, so we don't care about it. And so basically everything that counts is that this what's important is that the sine of pi t is positive and this omega is negative, and we have the radius that tends toward infinity. So negative here, infinity here, and something positive here, and something that you don't care about because it's bounded. So we have something of the form e to the minus infinity tends towards 0. Okay, we have the infinity, which is our radius r, the negative, which is our omega, because it's below 0, okay, and the sine of pi t that is positive. So at the end we have positive times negative times infinity, so negative infinity, so e to the minus infinity, and so the whole thing vanishes. And so that's what we wanted to prove. We wanted to prove that the second part, and the part along the circular axis, tends towards 0 as our radius r gets larger and larger. And so now we proved it. Again, you can substitute everything inside the formula and just again show that this e to the negative I omega r e to the pi t, that this can be written as e to the negative infinity, because that's an exponential decay, and the exponential decay wins over everything else. So you can of course write the dx in with dt everything else, and you can substitute the x squared with r e to the pi t, so r squared e to the 2 pi t in the denominator. But all you need to do is to prove that this part here, so the exponent can be written as e to the minus infinity, and that it goes to 0 as said, and so that the whole thing vanishes. Okay, that's the main part. So now we can use the residue theorem. We know that our counter integral is equal to 2 pi I times the sum of the residue. We know that the part along the real axis, or 1, is our original integral, because we go from negative to positive infinity. And we know that our second part vanishes as said, if the radius gets toward infinity. So we only have that our original integral plus 0. So our original integral is equal to 2 pi I times the sum of the residues. And so if omega is negative, our residue is this residue here, if you can still read it. So it's 1 over 4 times I to the times e to the omega times omega minus 1, okay, where omega is negative. And so if you multiply by 2 pi I, we should get negative pi over 2 times e to the omega times omega minus 1, okay. So the I times I makes a negative. So this I here times this I here is negative. We have a 2 in the denominator and the 4 in the denominator, so we have 1 over 2, okay, so 2 over 4, so 1 over 2, and we have our pi. So that's our final result if omega is negative. If it's positive, we do it in a similar way, but this time we need to go along the lower half plane, okay. So we still have our first part that goes from negative infinity to positive infinity, but then our circular axis is in the lower half plane, so where the imaginary axis is negative, basically, okay? So below the real axis. So again, the proof is quite similar. You know that the first part is your original integral. Now you want to prove that the second part, so this part number 2 goes to 0 as the radius gets larger and larger. So you can again substitute everything that we did before. It's the same thing. So you have x equal to r e to the pi I t and so on. But our t will be between 0 and -1, okay? Because as I said, we are rotating from 0 to -1, but along the lower half plane, not the positive half plane, okay? If we rotate from 0 to -1, along the upper half plane, it's from t is between 0 and 1, but if it's along the lower half plane, t is between 0 and -1, okay? And so again, then you can substitute everything else. You have your integral from 0 to -1 because it's with respect to t. You can again place everything else in the integral. But what's really important again is that we have our e to the minus I omega x, okay, where x is substituted with this r to the e pi I t. And so here in this case, we know that, so we have e to the omega r, we take the negative I inside, so we have negative I times cosine pi t plus negative I squared, so -1, so +1 times sine of pi t, okay? So again, we replace this e to the pi I t, this r to the e pi I t with r cosine pi t plus r I sine pi t, okay? And so then we let the negative I come inside, okay? The other negative I, okay? Yeah. And so now we know that omega is positive, and you also know that sine of pi t is negative for all t between 0 and -1, okay? Which would make sense because again, now we are in the lower half plane, so the sine is generally the part on the y-axis, and the y-axis here is always negative, okay? So the imaginary axis is always negative, okay? The cosine can vary, but again, the cosine here is bounded because there is a 9 in front of it, so we don't care about the cosine. So we know that omega is positive and sine is negative. So again, we have something e to the minus something, and again, r tends toward infinity. So we have again e to the negative infinity, which tends towards 0. Okay, and so yeah, so we know that our second part again vanishes as r gets larger and larger, and so we are left with our first part plus 0. So yeah, I plus 0 again is equal to minus 2 pi I times the sum of the residue. Why the minus 2 pi I? Because we are integrating in a counterclockwise direction. That's very, very important. I will even make a warning. It's minus 2 pi I. Why? Because here we have a counter integral, but we're going in this sense. It's in the clockwise direction. Sorry, we're integrating along a clockwise direction. If we have a counter integral with the clockwise direction, which is the case here, okay, we're doing like that, and we need a negative sign in front of the 2 pi I. Here in the other part, we're going like this, and so it's counterclockwise, and counterclockwise is positive, so we don't need a negative sign in front of the 2 pi I. Where was this part? Here. Okay, we don't need a negative because we have a counter integral that is counterclockwise. Okay, remember that counterclockwise means positive in math, and clockwise means negative. So here I said we have a clockwise counter, and so we need to have a negative in front of the 2 pi I to be mathematically correct. And so yeah, we have negative 2 pi I times the sum of the residue. Again, the residue is this time the residue at negative I and not positive I, because the positive I is not in our domain. And so we had the residue. Where was it? Or residue here was it. So 1/4 times r times e to the negative omega times omega plus 1. And so again, I said we have our integral plus 0. So our first part plus the second part that vanishes is equal to negative 2 pi I times the sum of the residue. And so if we multiply this residue here, so I said the 1/4 times I times e to the negative omega times omega plus 1 with the negative 2 pi I, we should get the following. So pi/2 times e to the negative omega times omega plus 1. Okay, and so again here we assume that omega is positive. Okay, so I hope it was clear. So the main thing to remember is if you want to evaluate the Fourier transform using the residue theorem, for the first part you go as usual. You have your find your poles, then you check if it's a pole of which order 1, 2, 3. 1 is easy, but greater than 1, it quickly becomes messy. Okay, true, it can still be done, 3 maybe, but 4, 5, 6, 7, and so on, that's hardcore, okay? So generally, you don't have a polar of order, I don't know, 89 in your test. That would be inhuman. But yeah, maybe your prof is a statist and he does it, I don't know. But yeah, generally we have something of order 1, 2, or maybe 3, but that's it, okay? So if it's of order 1, it's not discussed in this video because it's easy. It's easier, if it's order 2 or greater, you use the formula for pole of order n. So which is this formula here, I said, so it's, we already said it in at the beginning of the video, you should be familiar with it by now. So again, you compute your residues, and then you do a sign separation for omega if it's negative or positive. So depending on the sign, you will need another contour, and the contour can be determined by looking to which condition should be true to have an exponential decay at the end, okay, for the second part, so the part along the circular axis, okay. If we need to have, for the part along the circular axis, be it here or here, we need to have e to the minus infinity at the end. And so depending on the sign of omega, you need to be sure that the sign of pi t basically has the opposite sign, so that the whole thing is negative, okay. So if omega is negative, sign should be positive, that you don't have negative, okay, because if you had negative, we would have positive, and so it would not converge, we would not have an exponential decay, okay. We would have e to the infinity, which is infinity, so we can't really say something about it. So we couldn't prove that the second part, so the circular part, vanishes. And so I said if omega is positive, sign of p should be negative, because yeah, so we again have e to the minus something, and so that's why we choose this part, okay, because we're choosing basically the opposite, okay, because yeah, if omega is negative, we go in the upper half plane. If omega is positive, we go on the lower half plane. Of course, if you use another notation than the one I use it, so if you don't use e to the minus I omega x as your Fourier transform notation, maybe it can be different, okay? Because as said, there are several notations that are in use. But for my notation, this is maybe I think the most common one, if I remember well. Yeah, your omega sign should be opposite to the region where you are integrating. So if omega is positive, you integrate in the negative half plane, so below the real axis, and if omega is negative, you integrate in the positive half plane, so above the real axis. That's really the main focus on this video. So after that, you can prove that your second part vanishes. You set your x equal to r to the e pi I t. You choose between 0 and 1 or 0 and negative 1. Okay, again, depending on if you're going below the real axis or above the real axis. You have your dx, and then you replace everything with t in the integral. But again, the only thing that matters really is this exponent inside the exponent, because you have e to the minus I omega x, and the x will be replaced by this r e to the pi I t. And so again, you use Euler's formula. You replace this e to the pi I t with e to the cos pi t plus I sine pi t. This e to the pi I t, you replace it with cos pi t plus I sine pt. And then you prove that you have e to the negative something, and you know that the radius tends toward infinity, and so we get e to the minus infinity, and it's okay. So the radius is always positive. You cannot have a negative radius, okay? That's not possible, because the radius is a geometrical object, basically. I think you already know that, okay? The radius is always positive. You cannot have the radius as it tends to negative infinity. It doesn't exist because it's a distance, the radius, okay? So it's always positive. You cannot have a negative distance in real life, okay? Maybe if this was a confusion, now it is not, okay? So the radius is always positive, and so you need to make sure that your omega and your sine pt are of opposite signs. So it's you have a negative, and so you have e to the negative infinity, and it goes to 0, and so the second part vanishes, and you're only left with the first part, which is your original integral. and then you can use the residue theorem. Okay, that's really the main focus on this video, the sign of omega for the Fourier transform using the residue theorem. And then yeah, for the residue theorem, be careful that you only compute the residues for the pole that are inside your domain, because I said at the beginning here we had two cases, but only one is in the domain for each case. Okay, if you go along the upper half plane, you have only I. If you go along the lower half plane, you only have negative I. And so you only need to take those residues into account. Okay, that's really the important thing. And again, the minus 2 pi I or the 2 pi I, that's really an important thing. I think I forgot it in the last video where I did t over x squared plus 1 whole squared as the Fourier transform. I will maybe write it in the comments there. If you have a contour integral that is clockwise, you need a negative sign. If you have a contour integral that is counterclockwise, it is positive. That was mathematically established. There is no true meaning. It's just they said it is like that, and everyone obeys the rules. Okay, so if we go along the lower half plane, we are going clockwise, so we need a negative. Okay, that's why there is a negative here. Otherwise, it would be wrong. Okay. Yeah. So I hope it was clear. Yeah, thanks for watching. Yes.